So a little bit about myself. I'm a fourth-year student at the University of Waterloo, majoring in computational mathematics. And I'm currently working as a software developer intern at Deloitte DSpace. For those of you who don't know DSpace, DSpace is a prototyping team in Deloitte where we prototype using cutting-edge technologies and finding the tools that can potentially benefit Deloitte and our consumers, or our clients. So today our topic is about weak supervised labeling systems. So as we all know, in the last several years, machine learning system has explosion of interest, and with an estimate of over $12 billion of spending this year. And these machine learning models require a huge amount of training data in order to work. And research have shown they need at least tens of thousands or even millions to reach peak predictive performance. And labeling training data is increasingly the hardest bottleneck in today's deploying machine learning system. So how do we get label data is a question. Traditionally, we have the traditional way of supervision where we hand unlabeled data to subject matter experts, where we ask them to label the data. But that's very time consuming. That's very expensive. So what kind of approach have people taken with regard to that? So we have something so-called active learning, where we take a small portion of the unlabeled data and we hand that to the subject matter experts so that they can label a small portion every time, and that continues, and we eventually have a labeled data for the data set in this way, and it's less costly. And then we have a so-called semi-supervised learning, where we have a small portion of labeled data comparing to the unlabeled data, and we train machine learning models to find the correlations between data points and sort of mimic what labels look like in the labeled data, and to apply that on the unlabeled data. And then today we'll be talking about weak supervision. We'll be sharing about a tool that created by Stanford University. And we also have transfer learning, where models have been trained on other data sets. One famous example is BERT. BERT is very powerful. It has been trained on multiple data sources, huge data sets, and it performs very well on different types of text classification. But in our case, we're solving a problem for our internal clients, and a lot of our clients are from different industries, and they have their own domain kind of knowledge. And BERT doesn't perform as well on those, so we will have to create our own tool to sort of create labels for their data. So just to compare strong supervision and weak supervision.
So what is it, BERT?
BERT, B-E-R-T.
What is that?
It's it's a model that trained on multiple data sources for multiple use case. One use case is that you can use BERT to classify your text data. You don't have to train it, you just have to fine tune it for your own purpose, and it works really well. Yeah.
Do you know what it's called?
Sorry?
Full form?
Sorry?
Do you know the full form of it?
It's just BERT, B-E-R-T.
That's it.
Yeah, that's it. Yeah.
Bidirectional encoder for text recognition.
Yeah. Thank you. And just to quickly compare strong and weak supervision. Weak supervision is less costly compared to strong supervision because we don't need that much manpower, but it's less accurate because, yeah, obviously we're not providing as much supervision. And today we'll be sharing a tool developed by Stanford University in 2017. It's called Snorkel. So traditionally we give unlabeled data to our subject matter expert and ask them to label data. But now what we do, instead of doing that, we go to our subject matter experts and ask them to write so-called labeling functions that express arbitrary heuristics. That we use those heuristics to label our unlabeled data. And there are algorithms pre-trained in Snorkel that studies those label functions, and they sort of improve how the label function perform by adding values or weight to those label functions, and we will get a very well noise-aware label for our unlabeled data. So what are labeling functions? There there are different type of labeling functions, but the main focus of labeling functions is that we want to write some like really intuitive function to label our data using different ways. There are so-called external knowledge base, where consider it as a dictionary. Like for example, if one of our client is in the medical industry, and then there are dictionaries, pre-built knowledge base for medical. And if certain words appear in that database, then we know that we can classify our client's data using that kind of knowledge. And there's also something called a pattern-based labeling function, which we'll be discussing on the next page. And there also are domain heuristics labeling function, where we apply more internal knowledge. This serves more like specific clients. So what's pattern-based labeling functions? Considering we're building a model to classify celebrity investment, meaning that we try to go on Twitter and we try to build a model that find investment made by celebrities. In this case, we're using the URU Twitter account as example. I don't know if you guys can see this, but this is basically, I will read this out. It's the partnership between Snap Travel, a company, founded by URU alumni, one person and another person, and Steph Curry. Steph Curry is the investor in this company. And what, consider our model, consider the purpose of a model to try to find this kind of relationship. So what is a labeling function in this case? So consider our label to be celebrity investment, and our labeling function will be if you see a partnership word in the sentence, followed by a company subject, then followed by a celebrity subject, then label this as a celebrity investment. This is just one example of labeling functions. We can switch the order, or we can even make it more complex. But this is just a very intuitive way of creating labeling functions. In this case, partner, the word partner is found here, and Snap Travel, it's a company subject, and then we have Steph Curry, the celebrity subject. Then this sentence will get this label. So people may ask, how does Snorkel know which word is, how does Snorkel figure out the subject for each word? So Snorkel applies the Spacy, it's another NLP library that the industry is heavily using nowadays. So Spacy has a name entity recognition tool that allows users to find name entity, which is the subject for a word. So in this case, Google is labeled, or Google has the entity organization, and iPhone has the entity of product. So in this way, Snorkel really knows which entity to look for in our text data. So another kind of labeling function is domain heuristic, which we discussed earlier. It focuses more on internal knowledge base. So considering the same sentence, but what if University of Waterloo wants to train a model to find out all the tweets that are related to their math undergrad? Transfer learning or other tools won't be able to tell. Or because these are internal kind of knowledge base inside Waterloo. So we can build a function using the term BMath, which is used in Waterloo. BMath indicates Bachelor of Mathematics. So in this case, the labeling function is really simple. If BMath is found in the sentence, then I'll label the sentence as math undergrad. This is a domain heuristic labeling function. And so how does Snorkel work on the back end? So any questions here, guys?
So the label you enter it manually, or you extract the entity from Spacy and choose some high frequency one?
So you built the labeling functions, and you send them using you send those labeling functions to Snorkel. Snorkel already has a Spacy built in, imported.
Yes. So you just write the rules one by one?
Yeah. You basically just write out the rules, and Snorkel will do everything for you. It will apply Spacy's name entity recognition.
So what I understand is Spacy can have custom entities. We can create custom entities using Spacy. So can you use those custom entities also for Snorkel?
I'm not too sure about that, but okay, that we have to. I'm more than happy to discuss that later, but I haven't checked out the capability of fine-tune spacing in Snorkel.
Okay, I'll just give you an example. Like if I say my premium is wave, so I'm looking for the word wave,
Yeah.
but that's not a name entity. So how do I tackle that kind of data?
So we can create sort of called a candidate group in Snorkel, so that you can specify the exact word you're looking for. So for example, an example Snorkel use in their introduction a lot, they're trying to find a spouse relationship. So they kind of declare husband and wife and that kind of entity. I don't know if that addressed your question probably, but I think there's a lot of things you can do with Snorkel, a lot of customized stuff, but this is just the basic idea. Okay, so moving on, so how Snorkel works, we first create a pool of labeling functions, and then Snorkel will apply those labeling functions to the unlabeled data. And for each sentence, in this case we're using sentences as our unlabeled data, so for each sentence, Snorkel is going to apply from 0 to n labels. If zero apply means no label function is applied on that sentence. If multiple labels are applied to that sentence, it means either we have a conflict, meaning label function disagree, a label function under a different class disagree with each other on that sentence, or we might have multiple labeling function under the same class gets applied to the same sentence. So the first case, we have sentence sentence 1, and is then labeled as class A, meaning that one labeling function under class A gets applied to sentence 1. And for sentence 2, we have label ABC, meaning that one labeling function under class A, B, and C all get applied to sentence 2. And for sentence 3, we have 2 label A's, indicating 2 labeling functions under class A gets applied to sentence 3. So eventually Snorkel wants to give us one set of labels, like one label for each sentence. We're not allowing multi-class labeling for now. So what Snorkel does is that Snorkel has it's pre-trained, or it's you can fine-tune it, but applies a generated model which studies a correlation, a joint probability of input and output, in this case labeling functions and labels, so that it can know the importance of different labeling functions. So in this way, Snorkel is able to apply different weight to labeling functions, so that multiple labeling labels can become one label in this way.
Could you give an example, maybe just a simple example of how this might work for
Yeah.
students?
Sure. So in this case, using sentence 2 as an example, as you can see, sentence 2 is labeled by A, B, and C in the first iteration, which means one labeling function under each class gets applied to sentence 2. And Snorkel doesn't want that because and our final output should be one class per sentence, one label per sentence, right? So in this case, we have a so-called conflict, meaning that we have different labels assigned to the same sentence. We want to resolve that problem.
Maybe there are more than one labels.
Yes, exactly. But like for this example, what Snorkel usually do, Snorkel allows, I'm not too sure about the multi-label learning, multi-class learning, using Snorkel, but usually people use Snorkel to apply one label to one data. So does that address your?
So do you decide by which label is more important, or do you have confidence ranking when you apply a label?
So Snorkel, for example, you write 10 labeling functions for each class, and Snorkel will apply all of them. And there are no correct or wrong to those labels. Snorkel will purely depend their importance by looking at their or overlap and conflicts using their generated model. So Snorkel will assume they're all correct, and it will merge or combine them to one label by just studying their correlations.
Does it generate a new label?
Not necessarily, because in this case, A, B, and C become A. which
Well, what
mean-
if A and B are always together, and then you have A, B, and C, would it give you A and B?
In this case, again, we're only
Just,
considering like
only,
one.
I mean A, B, or just purely the labels you have defined functions for, or the labels it's going to give you?
In this case, if A and B are always together, it means that the two label class will have 100% overlapping
Right.
rate, meaning that the two classes are exactly the same. I think what Snorkel does is either gets A or B in this case, because eventually we only want one label per data point.
Would it use maybe the context of the sentence or something, or?
I mean, that really depends on the different type of labeling function you create, right? But this is just the simple flow of Snorkel. Yeah.
So what is the generative model doing?
Okay, so usually nowadays when we train our predictive model from X to Y, giving X, we want to know the probability of Y. That's a discriminative model. So what a generative model does is that instead of looking at the probability of giving X was the probability of Y, the study is the drawing probability of X and Y, which we can use equations to derive the probability of X giving Y, which is the opposite. So in this case, we have labels in our labeling functions, right? So by looking at the overlap and conflicts of our labeling function labels, they are able to derive how to apply weight to different labeling functions. Just by looking at the relational probability. Does that?
What if your data set is not balanced to start in terms of, label distribution?
Yeah.
Ground truth label distribution.
That's a very good question. So before applying Snorkel, I was like, what we do is that we make sure our data set is fine-tuned enough to apply Snorkel on. So yeah, that's Snorkel. I don't think Snorkel can fix that issue well, but I might be wrong.
Because that way you probably end up maybe with B not existing at all, because
Exactly.
it always says it's unlikely, it's unlikely, it's unlikely, because the other
Exactly.
one appears more often.
Yeah, that's actually an issue I'm gonna address later, where Snorkel heavily depends on how informative our label functions are. So yeah. So can we move on?
No.
Go back. So, how good is Snorkel? According to the research paper, Snorkel is able to match the performance of hand labeling by having users create tens of labeling functions. And the hand label process might take weeks or a month to do. But again, this heavily relies on how well informative our labeling functions are and how well our distribution of our data is. So here we ask ourselves, Snorkel is very good, but why don't we use Snorkel? In our case, we're trying to create classification models for our internal clients. And our internal clients' data heavily rely on domain heuristics. If you don't remember, domain heuristics is basically their internal knowledge. So what we're trying to do doesn't require that complex labeling functions. We're only using the simplest kind of labeling function, which is if you see certain words, then label the sentence as such. So we don't really need Snorkel because Snorkel gives you the capability of using those complex label functions. But and also our subject matter experts in this case are senior consultants. Their time are very valuable. So training them to understand what labeling functions are and how to create informative labeling functions is also time consuming. So we ask ourselves, how can we simplify the process of generating labeling functions? Instead of having our project owners to create labeling functions. So here we present you with Astron. This is a tool that our team built. Astron is a Greek term for stars. There's a story behind that, but I won't explain it. So the flow of Snorkel is that we have our data, 0% labeled. And then we give our data to our subject matter experts, in this case our project owners. We ask them to label a small portion of it. We haven't decided the percentage, but we have tried different percentages, which I will show later. So after having them label these, this portion of the data, we pass it on to the Astron model, and Astron is able to generate additional label data for the data set. So the idea is really simple. But like today I can't really show you guys how it performs on our internal data because it's confidential. So I'm just using a news category data set from Kaggle. So what this data set contains is just newsletter headers and abstractions. We combine them together so we only have one column for the information. And the other feature is label is just news categories. We have there are more than 30 news categories in this data set. So yeah, of course, data preparation. As we mentioned, text data, raw text data. Machines can't understand them just because there's so many variations of language. So what we do first, we apply lemmatization. Lemmatization is basically to find the root of words. So in this case, playing, plays, played, all gets mapped to play, so that the machine can really understand what's happening here. So here's an example. The boy's car are different colors, gets mapped or translated to the boy car be different color. So then the machine can actually find a pattern in the words. So they're not that there are not many variation words anymore. So something else is removing stop words. Stop words is basically the words that doesn't carry a lot of meaning. But again, this really depends on the scenario where, like the different scenarios we're looking in. Sometimes stop words can be informative. For example, what or which can change the meaning of the sentence. So we really need to think about removing stop word. Like sometimes we don't want to do this, and sometimes we do. And to move on to the coding part, we import Spacy again, and really good NLP tool. And we also import regular expression just to fix the characters. So we first send all characters to lowercase. So it won't be case sensitive. And then we take out the stop words and lemmatization. In this case, we're taking out stop words because for newsletters, headers, and abstractions, stop words don't really carry a lot of meaning. And then finally, we remove non-alphabetic letters. I'm showing this here because the order really matters. Like one time we removed, at first we tried to remove non-alphabetic letters before removing stop word, and that gave us an issue where, for example, we have an internal client that one of their project has abbreviations. For example, U.I.S, that kind of thing. And when you remove non-alphabetic letters, you're left with the character U, the character I, and character S, and those get removed. But those are really important information that we want to keep. So we decide to go with this order. So for this research purpose of demonstrating the performance of this tool, we decided to separate this news category data set into multiple data sets, so we can take the average of the performance. And within each data set, we separate it into train and test, because we're interested in know how the size of labeled data can influence the performance. Just a quick reminder, the training data indicates the amount of data we want to send to our subject matter experts to label, and the test data will be the unlabeled data that we want to apply this model on. So one of the examples is data set K contains class world news and taste, and we try to pick up, again back to the point where we want to have equally distributed data. So in each separated data set, we try to keep the two classes really balanced so that the process, So this is the performance of different training set with the performance regarding to the training set size. So we have two variables that we look into. Two statistical variables that we look into. First is called total coverage. We're interested to know how many labels in the unlabeled data are labeled by this whole process. And we're also interested in knowing how, what percentage of that labeled data is accurate. So using an example here, so the test set again is on label data. We send label data to our, we send a small portion to our subject matter experts to label, and this is a portion that's left over. This is the on-label set. So in this case, we have 100 sentences that are unlabeled, and we apply this model to this 100 sentences. We get 25 sentences with label, meaning that 25 sentences have, this 25 sentences indicates a total coverage of 25% in this case. And then we look into the 25 sentences, and we compare them with the actual labels, because in this case, we're using a data set that has correct labels, so we can check their accuracy. So in this case, if 20 out of 25 sentences are correctly labeled, then our accuracy in this case is 80%. So we test out training set, which is the portion to label, from 50% all the way up to 1%. So in this case, we will know how much label we can send to the subject matter experts. So we took an average, and we see from 50% data training to 1%, and here's 5%. The performance is better because we have an overall decreasing trend in our average accuracy, and we have an overall increasing trend in our coverage. So that we really want to find the point where the two lines meet each other. And this is when we have 5% training data. We achieve 18% coverage and 80% accuracy in our on-label data. And this will depend on the size of the data. But in this case, we're using a data set that has 5,000 sentences on average. It will need further studies to show how well it performs on larger data sets. Yes.
What's the x-axis and the y-axis?
Oh, sorry. The y-axis, it's accuracy and the coverage. It's percentage. I can't really show the percentage because those two have like different scale. So I just want to show the overall trend and where they meet.
And the bottom?
The bottom is just training set. The size we want our subject matter experts to label.
So what is 0.5?
50%.
Oh,
So we start from 50% to all the way up to 1%.
Okay.
So it performs best at like 5%.
Training set is 50%, so test set is 50, or?
Yes.
And is that the accuracy of on the test or training?
That's the accuracy on the test.
Oh, okay.
Sure. Yeah, because we have labels here and we want to see how well it performs on label data.
Right.
Where does the coverage get worse when you label more?
The coverage, this is the coverage. The coverage actually gets better when we label less.
Yeah. So.
Yeah, at first it appears to be pretty weird to me as well, but later I realized that if we have a large training set, a large training set that we get our label function from, sometimes the sampling is so biased and the labeling functions are heavily overfitted on that training set. So it doesn't cover a lot of, it doesn't get a high coverage on the test set.
So is it the same test set, or do you change it with the training set size?
It's the same test set. We're using random sampling, but the state of the random sampling stays the same. So every time for different training set.
So if you have 100 sentences,
Yeah.
You use 50 of them for the first point for training. Would you use the other 50 for test?
Yes.
Or you still use whatever 10 for test?
We use the rest, the 50
The rest of the
Yeah.
other, so it's not the same test set then. But it should be much more accuracy and coverage if the test set size is increasing.
You're saying that if the test set is increasing, then the
So if you have more sentences that you're testing on, you're more likely to make a mistake, which means your accuracy should go
Yeah.
down and coverage should go down.
It's actually, the accuracy actually goes down when we
Right.
have more test set.
Less training is
Yeah.
probably the code.
Yeah, but okay, so this average coverage, I'm not able to show the scale here, but the actual coverage actually fluctuates between here's 50% and here's 20%. So the fluctuation is really small. So the coverage isn't fluctuating from like 10% to 80. It's like fluctuating between 50 and 20. But the accuracy fluctuates from here's 80 and here's like 5%. Like or yeah, the scale is different. My apologies. I'm not able to show the scale here just because I want to focus on the overall trend. But yeah.
So will there be data leakage? Like you just split into like you tune your model based on the test setting that. Normally you should have like a training, validation, and the test don't touch it.
Yeah.
It's like did you do that?
Yeah. Actually, we didn't do that just because we want to keep this process as simple as possible by taking the average, so that instead of doing validation set on like one data set, we try to take the average of multiple experiments to see the average performance. So in this case,
I didn't really have data leakage.
because we're not like this doesn't work similar to our normal machine learning model. Normally we train our the weight of our knots, right, to improve the whole model. But here we're actually getting labeling functions from our training set.
I think there would be leakage if you use the test set to choose which model to use later on.
Yeah.
But if I don't think they're doing it this year.
So you don't change
Every
the
time
function.
they're separating the set into test and training. Training on the training set,
Okay.
and then seeing how well it does on
Yeah.
the test set, and then reporting that.
Okay, so you didn't change the function based on the.
We did not. We did not.
Just to make sure I understand, so the training set itself is generated by the labelers, by the labeling functions. So you write the labeling functions, and then you apply them to 0.5 or 5% to create your training set.
Sure, no. So like this model actually doesn't do that because we realize creating a labeling function is not an intuitive kind of thing for our subject matter experts to do. So what we end up doing is that we actually send that small portion of unlabeled data to them and ask them to label that small portion of data. And we generate a labeling function automatically from that labeled data.
And then when you use half of your data for training set, what labeled that training set? The auto-generated labeling functions?
No, okay, using this as example, when we have a 50% training set, since we already have correct labels in this case, so there's no...
So these are manual labels by the subject matter experts?
No, this is a data set that I got from Kaggle, so they already have labels.
Okay.
It's just an experiment to show how well this performs. So in this case, using the example of having 50% training set, meaning that we use 50% of the data to get labeling functions. And we use those labeling functions to apply to the rest of 50% that doesn't have labels.
Okay.
Does that make sense?
And that's why you don't need validation here, because you're not validating a machine learning model, you're validating the accuracy of the generated label functions on the test set.
Yeah, I worry like he generates the labeling function based on the training data. So I'm worried about it. Yeah.
Excuse me. For the case, I think I missed this one. So it's indicating the true positive rate for the classification, for the labeling.
Oh, you mean the
Like how
accuracy?
many? Yeah, for the accuracy. What kind of accuracy?
Okay, so here we have around 80%. I think here starts from 70% and goes up to 80% and stays at 80%, 85 something, and decay to 80% with 5% training data, and then it starts to decay really quickly.
Indicating how many?
You mean by how much?
No, not the numbers. I mean accuracy here is indicating the how many labeled.
Within the labeled data, with the additional labeled data, what's the accuracy? Like we compare the labeled data to the actual labels.
Yeah, I'm asking this question because you mentioned that you may suffer from imbalanced data, right?
Yeah.
So sometimes accuracy can sometimes be misleading if we have this problem imbalanced label.
In this research, we make sure that every data set we have balanced data. So we really, so to this slide. So in this data set K, for example, we have world news and case. Both of them have around 2,100 sentences.
This is during the training, right?
This data set is separated in training test, so performing that on this data set. We make sure that all separated data set have balanced data.
Yeah, because you mentioned the accuracy is like for the test set.
Yeah. Sorry. Yeah. So we use a stratified option for train test split, so that the data distribution in the train and test are really similar. Yeah, they have the same kind of distribution in both, so that we want to. Yeah, that's a good thing. So.
Can we move on?
Thank you. So, how does the back end of Astron work? So we have, using the previous result, we have 5% sentence for our subject matter experts to label. And then we generate labeling function from that 5%. And then we send our labeling function to, we have a labeling function pool. That the labeling function pool is applied on the rest of unlabeled data. And then, as for example, this 95% of unlabeled data, 10% of this 95% get new labels, and we assume those 10% have correct labels. And we want to generate new label function from that additional 10%. And this process continues until we can generate more labeling function. We have something called a labeling function filters, where not all, where we take away labeling function that disagree with each other. This is just a very simple process that we tested out. There are a lot of improvement that can be done here. There's definitely a lot of fine tuning for getting labeling function and applying them, but we're just trying to test out the whole kind of flow to see if it works. So does this sound intuitive?
Do you create the filters or?
Yeah, so the creation of this filter is basically based on the statistical study of the whole flow. So we have a matrix that keeps track of the statistics of each labeling function. We have coverage, overlap, and conflict for each labeling function, meaning how many sentences are applied on, how many conflicts they have with other labeling functions, and we have different threshold here to get rid of labeling function that we consider to be bad. Yeah.
Do you have examples of the generated labels?
Yeah, I will show it later.
Patient.
Okay.
Making it more interesting.
So what does a labeling function and what do labeling functions in Swarm look like? Right now, we're only in version 1, so just to really test out the whole process, we're applying n-gram heuristics, which means if you see, for using bigram as example, bigram is just 2 words. If you see 2 words in a sentence, no matter the order, apply this, apply a certain label to this sentence. So, for example, if we have education as a label, and one label function under education is teacher and school, then if we find teacher or school, teacher, school, school, teacher kind of appearance in sentences, we label it as education. Very simple.
It must be exact match, right?
Yeah, exact match. And this is how we generate, how the tool is able to generate labeling function each stage. The first iteration, we're using the data set of containing style, science, world news, news articles. So this is all automatic. We just label that 5%, and the first iteration, the tool is able to generate these label functions, and the coverage on the test set is 9.4%, and the accuracy is 86%. So using example for style, there's look good labeling functions, and for science, there's high energy space shuttle labeling functions. For the second iteration, we try to find new labeling functions from these 9.4% coverage. We don't know about the accuracy. We only know about the accuracy because we have the correct labels. But when it's actually running, we assume the 9.54% are all correct, and we generate a label from that labeling function from that 9.4%. So what we have here like the automatic generated labeling functions are fashion week, beauty list for style, and we have study suggest, study show for science. And then this process continues until we can't get any additional labeling function for each class, for all the classes. So the final iteration in this case, we have researchers say for science, but no other labeling function generated for other two classes. And yeah, we achieved 15.8% coverage and 68% accuracy.
86.
Yeah, sorry. Yeah, thank you. Where in our case, our objective is to achieve high accuracy rather than high coverage, because we want to make this as weak supervised as possible. We don't want to spend time like investigate and label sentences. So we don't really care about coverage as long as there are additional labels for us to use, at least. So yeah, this is the result where the total data set has 6,600 sentences, and we have 300 of them labeled, and it's able to generate an additional 1,000 sentences with 86% accuracy.
The labels are manually used, right?
Yes,
By
the
accident.
labels are. Yeah, we're pretending it's manual labels, but we actually have.
Manually labeled
Yeah.
on tablet.
Yeah. So, what are the potential use cases for this tool? We initially we thought about active learning, but the challenge of active learning is that the first iteration of active learning, we really want to get the informative data so that active learning really works. Or else active learning, if the first iteration contains noisy data, then active learning will end up with noisy data. So we can use this tool to sort of generate the sample for active learning. How does this work? I will give you a really simple example. So for example, we want to, instead of classifying sentences in our data frame, think of we have multiple documents. We have like 1,000 documents and multiple sentences within each document. And we want to label those documents, label the sentence within each document. So what we can do is that we apply this tool to all documents, all the sentences within all documents. And then for the documents that have more labels, like we rank them by the coverage, by the percentage of labels applied to each document. We get the top, let's say 10%, and we also get the top 10% for the document that has the most coverage, meaning a lot of labeling functions disagree in that document. And we can use those sampling to send to, those documents to send to active learning for subject matter experts to label. So that in that case, we know we're using informative data for them. And this can also help us analyze our data. So what StoneCode cannot do is that StoneCode can't show you, there might be a way, but like currently we haven't figured out a way to use StoneCode to keep track of how each labeling function is applied at each iteration. And using this tool, we can take control of that. We can gain insight to our data, and it can potentially serve as a data mining tool for ourselves. And it's really simple to use. We don't have to train our subject matter experts to learn about labeling functions. And the next step goals for this tool is to investigate a multi-label classification. Yeah, back to the point where multiple labels can be applied to one sentence. We want to investigate in that. In order to achieve that, we might want to consider generate more complex labeling functions. How can we generate more complex logics from the labeled data? And the final goal will be to improve the tool's backend. And yeah, and there are also other research projects that are related to this topic. So for those of you who are interested, IBM has come up with a research paper called LASL. It's for image classification, but it also tells you how to generate additional data when you don't have enough labeled images. And there's also advanced semi-supervised learning with supervised data augmentation like Google. Won't go into details, but it's pretty cool. Yeah, so that's pretty much it. Thank you guys. Any questions? Feedback?
So with the example that you gave with, you had fashion, you had science and world news, and over the iterations, as you were going through them, I kind of noticed your coverage, increased to about 15%, your accuracy was about 85%, and those words seem to get a little more general as you go along. So I was wondering, you had mentioned thresholds and filtering before for those labeling functions. If you wanted something that was more specific, more accurate, you could set those thresholds to essentially target your more specific words, right?
Exactly. There are multiple ways of doing that. Like right now, we're only generating bigrams for our labeling function, and this is really simple. We're not, in this case, we're not focusing on getting high coverage and high accuracy. It's just a demonstration of the whole flow. But yeah, of course, we can change the threshold or how our labeling functions, the logic of our labeling function to achieve better outcome.
Yeah, so if you wanted to, for example, in science, you have, like physics, biology, chemistry. If you wanted to target specifically physics, you wouldn't want your coverage so high, you want your accuracy a little higher, so you could focus on something like high energy and, space shuttle for space and physics. But then if you wanted to go a little more general, you can increase that coverage and decrease the accuracy.
Exactly.
Right? Okay, cool.
Yeah, there's a lot of play around. But yeah.
Do you use, when you decide on the, the value or the importance of a certain combination or a certain bigram, do you weigh it by which iteration it was found in, since it does affect the generality of the word or
Okay,
the combination?
so in this version 1, we're assuming that every iteration, all additional sentences are labeled correctly. So we're not applying the labeling function in the second iteration on the sentences that are already labeled in the first iteration. So
so if you find something in the first iteration, could it be more specific and so has more weight in terms of the science, for example, criteria or the science label, than something in the fourth iteration, and so you can give it more, you can instead of making them all the same weight, now they can be weighed by when it is that you discovered them.
exactly. Yeah, I think that's a very good point. So because
so researchers say, for example, is less science related than maybe high energy. It's also, it kind of measures how unique it is or the information gain you get from.
Yeah, I think this is kind of a tree flow where a node of high energy and the third child of it becomes research and suggest.
Yeah, it seems to.
So yeah, there's definitely a lot of improvement that can be done to this tool, but again, our initial idea is just to test out the whole flow.
One more question.
Yeah.
Have you tried using embeddings instead of the exact words? I know it will mean different ways of creating your functions, but if you try and fall back on an embedding, then you might need to do less pre-processing in terms of removing stop words, in terms of turning all capitals into lowercase. It might take care of that for you. Have you tried that?
Not for now, but we'll definitely look into that. Thank you for the suggestion.
So how many use cases you have already tried? Like, so currently like a general model, but for different use case, maybe you need to tune the parameter. So how much work it will, so
Okay,
it's
so
quite different.
right now I can't really go into details because it's confidential, but I will just give you so right now we have created our label sentences using this, like a similar approach with this, and we are sending them to our subject matter expert. So we haven't tested out how well that's going to perform. I can get back to you later about how well that performs, but we're at a stage to really test how well it performs.
These are words in a sentence that you're using to go and determine your label?
Yeah.
Have you looked at proximity? Like not necessarily in the same sentence, but, you know, words near other words that would give you clues in terms of, for example, I see you got North Korea, South Korea as world news, but South Korea has a bunch of other stuff that's going on too, that could be entertainment or science or whatever, but you wouldn't necessarily be able to tell it from an individual sentence, it would be in the context of material around it.
Exactly. That's something called I think we actually discussed about that. That's called a pattern-based labeling function, where Snorkel gives the user the capability of writing that. But since we're automating the process of generating labeling functions, we haven't come up with a way to creating those labeling functions. But definitely, they will perform better. But we have to figure out a way to generate those.
Have you looked at graph databases at all for that?
Yeah, we're actually using graph database to find the relationship between.
Okay.
Yeah. Thank you.
Last question.
If you use kind of those generated labels then in downstream models, isn't that in many ways pretty dangerous because you kind of extract kind of the obvious cases, right? So you kind of generate a new labeled data set with kind of obviously correctly labeled things. And all those corner cases where it's not obvious which category they belong to, those kind of, as far as I understand, you probably don't label those and kind of don't use those in the upstream models. But aren't those kind of the actual interesting ones where the downstream model might kind of actually learn to differentiate and to learn kind of what the real difference actually is?
Exactly, that's a very good point. That's why I mentioned we want to run this parallel with that active learning, where we use the amount of data that this works well on, and as well as the portion of data that this doesn't perform well on. So then we can use active learning to
So would you then basically send back those examples where the simple labeling doesn't work back to the domain experts to kind of relabel those? Okay.
Yeah, that's a very good question.
Thank you very much.
Thank you.